Yeah, so good morning, everyone. Does anybody know what gravel cycling is? Yeah, I've just been in Spain doing a few days. It's like off-road riding. It was beautiful. But now I'm really happy to be here in Dublin and talking about something else that I'm really excited about, which is eBPF. How many people here have come across the term eBPF before? Pretty good show of hands. Excellent. I've been kind of involved in eBPF and how we're using it in the cloud-native environment for quite a few years now. And I'm hoping this morning I can share with you some of the reasons why I'm so excited about it and some of the ways that it can be of practical use for SRE activities. I'm not an SRE myself, but I hope that the kind of engineering information about eBPF will be really useful to you in your day-to-day roles. So, as I say, I'm pretty excited about eBPF, and it turns out I'm not the only one. There's actually a documentary coming out that's being, it's being screened at KubeCon in Chicago in just under a month's time. So do look out for that. You can find the trailer on YouTube, and it's really cool. Okay, so I've also written a couple of books about eBPF. I'll share some links at the end where you can download these. What is eBPF is really the high-level introduction to what this technology is and why it's so important. And the Learning eBPF one, I honestly think most people in this room will never need to write eBPF code. So you may never need that book, but if you want to dive deeper, there it is. So people often say, what does eBPF stand for? And the acronym kind of stands for Extended Berkeley Packet Filtering, but we've stopped really using that acronym now because it does so much more than filtering packets that the acronym's pretty much misleading almost now. What eBPF allows us to do is to load custom programs into the kernel so that we can change the way that the kernel behaves. We can dynamically program the kernel. Let's make sure we're all up to speed on what we mean when we talk about the kernel. It's the part of the operating system that interfaces with hardware. So if you have an application that's writing to a file or receiving a network message or even allocating memory, all of these things involve hardware. And the applications can't do it directly themselves. They have to ask for assistance from the kernel. Most of the time, application developers don't know about this. They don't need to care because it's all taken care of by programming language abstractions. But the kernel is always involved when we're doing any of these activities that touch hardware. The kernel's also coordinating all our different applications that are running at the same time and looking after things like privileges and permissions. So with eBPF, we can load a program into the kernel and we can attach it to some kind of event. And the event could be pretty much anything. It could be the entry point or the exit from any function in the kernel. It could be system calls. It could be different points where a network packet progresses through the networking stack. There's an almost unlimited set of places that we can attach our programs to. And then we can use that to either observe the fact that that event happened or maybe influence and change the behavior of what would have happened at that event. So I want to show a quick demo to start with. There are a few demos this morning, so let's hope that the demo gods are with us. So let's change this so that it's live. So hello SREcon. So what this little bit of code here is my eBPF program, and all it's going to do is write out some trace. And I'm also going to there's a bit of code here to sort of manage my eBPF program and load it into the kernel, and it's going to attach that program to the execve system call. That system call, don't worry too much about it if you've never come across it. It's just what is used to run a new executable. So every time a new executable gets run, this program is going to get triggered because it's attached to that event. And then there's a line here to actually write out the tracing. So if I run this, hopefully not too much happened. Oh, is sound gone? I don't think it was. I influenced more than I expected. Testing. I can't. Oh, there we go. I'm back. Okay, good. That was an unusual demo failure. All right, so if I run anything now on the same virtual machine, we should see my line of trace appear. And doesn't matter what I run, that shell was previously running already on this virtual machine, but I've been able to instrument it with my little Hello World program. I mean, it's not exactly exciting, it's not really very useful, but I hope that gives an idea of how I can dynamically kick off an eBPF program. And it also had some, actually let's do one more thing while I run that. If I run PS to look at the processes on that, well, in this shell, we can see the process ID here, 3189, appears in the tracing. And that's because the eBPF program has some knowledge of the context in which that event was triggered. And the fact that the eBPF program can get this contextual information about what triggered the event means we can maybe capture some of that information and use it to report interesting information. Which takes us on to the first practical use, I think, for eBPF in the world of SRE. And this is the ability to trace out different events across a system. I'm sure a lot of you will have already come across the BCC project and a lot of the observability and tracing tools that Brendan Gregg did a lot of work to popularize. When I first saw this diagram, I will confess I was pretty scared and horrified, like, what is all this? And really what it's trying to show is across that whole system, we can instrument and observe and trace out events from all kinds of different aspects of the system. You know, we can trace out events that relate to memory, you know, how many processes get killed. We can trace out events that relate to file usage. We can get information about, I don't know, what system calls are being triggered on my application. So across the whole system, we can use eBPF to get insight into what's happening. I'm going to use OpenSnoop as an example, so it's just one of many, many tools. And these have been around for quite a while now, so they're pretty well established. What OpenSnoop allows us to do is observe files being opened. So I find my OpenSnoop window and just run that. And we'll probably see a whole load of file accesses happening that are just to do with my virtual machine running on my laptop. But we could also, let's say we try to look at the etc. password file, and we just about catch it there in OpenSnoop before it scrolls off the screen. Oh, it did. Yeah, there it is. And we also saw, as cat was starting, it actually opens a whole load of other files, which kind of makes sense because it's using some of the C shared libraries. The point here really is that using this very simple OpenSnoop tool, we can get visibility into all of the file open events that are happening on this virtual machine. So that could be pretty useful. Okay. Now, I talked about the fact that this is dynamically changing the way the kernel behaves. And now that you've seen a couple of examples of it, let's step back a bit and think about why this is important. Now, if you want to make a change to the Linux kernel, well, first of all, it's actually really difficult. Like, kernel developers are experts in their field. There's tens of millions of lines of code in the kernel. And if you wanted to change the way the kernel behaves, you'd have to convince the community that that change was relevant to everyone. even if you then made the change, got it into the upstream kernel, it takes years between a kernel release being cut and it actually making its way into the Linux distributions that people are using in production. It can easily take 5 years for the kernel version to make it into certain Linux distributions. So if you want to make a change to the kernel, it's a long-term plan. But maybe you have a reason why you want a bespoke change to the kernel. eBPF lets you do that dynamically. You can just write the eBPF program that creates the behavior you want, and you can load it into your kernel immediately. Obviously, it's not affecting everybody else in the world, so you don't have to convince the whole upstream community about it. You can change the behavior of the kernel in your own bespoke and custom ways. You might be thinking, but I've been able to do that for years with kernel modules. And the thing is, I mean, how many companies, how many organizations here are happy with the idea of using kernel modules? Do we have people who use kernel modules here? I'm not seeing any hands, and the reason is that kernel modules, a bug in the kernel brings down the machine. And no offense to any kernel module developer, but all software has bugs, and if you have a bug in a kernel module, you do risk bringing down your machine and possibly your fleet. With eBPF, we have a process called verification, which analyzes the program as it's being loaded into the kernel and makes sure that it's safe to run. So it checks all the possible paths through that program, makes sure that memory access is going to be safe, that there's no null pointer dereferences, so it can't, which would typically crash the kernel. It's also going to make sure that that the program will run to completion, that it doesn't get into a hard loop. And this verification process is really the thing that differentiates eBPF programs from kernel modules and makes them much, much safer. Which leads me to my next practical example, which is the idea of mitigating a kernel vulnerability by loading an eBPF program. And the example I'm going to talk about is a packet of death vulnerability. So this is, imagine a kernel vulnerability where a particular form of network packet is going to cause the kernel to crash. Maybe there's a length field in a network packet that's 0 when it shouldn't be, and the kernel, for whatever reason, has a bug, doesn't know how to parse that packet properly, and crashes. So if you're an attacker and this vulnerability exists, and vulnerabilities like this have existed, you can craft a packet to be in this particular format and send it to a vulnerable host and bring that machine down. So prior to eBPF, what you'd have to do is get a kernel patch and apply that patch to your fleet of machines. With eBPF, we can load a very simple program into the kernel that will inspect the packet and just throw it on the floor if it matches the definition of this packet of death. And the code to do that would look something like this. We'd have a program that's attached somewhere in the networking stack. The program would look at the structure of the packet, make a decision on whether it's a packet of death or not, and drop it, throw it on the floor. If it's not a packet of death, it would pass it on up the networking stack as usual. Now, my little example here says if the protocol is IP proto ICMP, which I'm sure a lot of you know it's a ping packet. So I've got a little example to kind of show the principle of this, where what we're going to do is trace out ping packets. So here's my network program. Don't worry too much about the details of this, but basically here, if we've got a ping packet, we're going to write out a line of trace, and at the moment we're just going to pass it on as normal. So let's run that program. Hopefully that's running. And if I just ping localhost, so up here we see every second a ping message successfully being sent, and we can see the sequence numbers going up, great. And we can also see the trace lines happening here that's being generated by my eBPF program. Okay, so now what I'm going to do is change this to drop ping packets. And I just need to stop and restart this. Okay. And what we see is immediately the sequence numbers have stopped incrementing here. So we're still seeing the tracing being generated because the ping packet is still, the request is still being generated. It's being intercepted by this program, it's being dropped, so we never see the response. And that's why the sequence number stops incrementing, because we never get the reply to that ping. And just to kind of prove that the sequence numbers are still going up, if I change this back again and restart it, we should see, yeah, okay, so something like 40 packets got dropped, but now they're being successfully sent again. So what I've done there was dynamically change the networking behavior on that virtual machine with a very trivial example. But hopefully that kind of shows how you could use eBPF to mitigate vulnerabilities. Another example, there's a talk that Daniel Balkman did about using eBPF to mitigate Spectre vulnerabilities. And this is so much quicker and easier than having to apply a kernel patch. Now let's move on to thinking about how eBPF interacts when we're in a containerized world. How many people here are using Kubernetes? Quite a lot of people. I think a lot of people are using Kubernetes or containers. eBPF has really revolutionized the way that we can build infrastructure tooling, security, tracing, networking, particularly in cloud native. And I hope that what I'm about to show you will explain why. So when we run our applications in Kubernetes or some kind of containerized environment, our applications are running in containers. In Kubernetes, those containers run inside pods. But on a given virtual machine, or bare metal machine, if that's what we're using, there is only one kernel. And as I showed before, we're using that kernel every time hardware is involved. So whenever our containerized applications are accessing the network or reading files, or whenever Kubernetes is creating new containers, all of these things are involving the kernel. And it doesn't matter how many different pods we've got running, how many different containers we've got running, on that virtual machine, or bare metal machine, there is only one kernel, and that kernel is involved in all of those different applications. So if we have eBPF programs running in the kernel, it can observe and affect everything that's happening on that host machine. That means we can instrument whole systems by instrumenting per machine, and we don't have to make any changes to applications or the way they're configured. This little cartoon is now a few years old, but it's really great, I think, from Nathan. Kind of the idea that eBPF is going to supersede the sidecar model. So when we use the sidecar model, what we do is we have a container that provides our instrumentation. So maybe that sidecar is providing tracing or logging or security or whatever other functionality we want to add into all our applications. We add that functionality by injecting a sidecar into every pod. Now, pods are deliberately isolated from each other. That's the whole point of containerization, is we've separated out our applications so they can't interfere with each other. So if we're using sidecars, we have to inject the sidecar into every single different application. And we do that by changing the YAML that defines that pod. We probably don't do that manually. It's probably done somewhere sort of in the automated, either during CI/CD or during deployment. But there is an injection of that container into every application pod. That means that the sidecar, the instrumentation, is bound up with the life cycle of that application. If you want to change the instrumentation in the application, you're going to have to restart the pod. If we were using eBPF to provide our instrumentation, we don't have to change the definition of that application. And just like you could see my network example affecting the way that ping packets were being handled, I didn't have to restart ping. All I had to do was change the eBPF program. The same is true for any kind of eBPF instrumentation. We just change the instrumentation in the kernel, and it immediately has visibility over all our applications, whether they're containerized or not. Also means that if there's any malicious activity running on the node, it's visible to eBPF. If you have a malicious, somebody has injected something into a host that's maliciously opening files, then if you're running OpenSnoop on that host, that event will be visible to you. You don't have to rely on your attackers adding your logging and tracing into their attacking code. So, the fact that we can instrument by node rather than by individual application opens up the opportunity for a whole new generation of cloud-native tools. Let's have a look at a few examples in the observability space, because observability is essentially fundamental to everything that you do in SRE. First example is something called Inspector Gadget, and this takes those kind of, a lot of the event tracing that I showed that big confusing diagram of, a lot of those brought into the Kubernetes world so that we can add information about the Kubernetes context. So not just that a particular file is being opened in this file opening example, but also what's the node, what's the namespace, what's the pod that's involved, because that's going to be essential if you're trying to debug a problem. So I think I have an example of this running. So yeah. So trace open is very similar to OpenSnoop, except adding in the Kubernetes context. And if well, let's just have a look at the pods that are running so you can see I've got a few pods running on here. And if I exec into one of those pods and try and look at the etc password file again, and we can see not only does Inspector Gadget spot the access to that file, but also spots a whole load of other file open events that are related to that request. Okay. Other way. So the important point being that not only do you get visibility into these events, but cloud-native tooling can add this contextual information that you need to understand which pods and which containers are involved. Another example of an observability tool in the cloud-native world is a project called Pixie. Pixie lets you run lots of different eBPF tools across your cluster and then aggregates the information and gives you nice graphs and visual representations. This is just one of many possible examples from Pixie. This is showing CPU usage across an entire cluster. So flame graph collecting data that's been gathered by eBPF and pulling it together into one central place. So these kind of tools are really powerful ways of getting observability into what's happening across Kubernetes clusters. We can also use eBPF for high-performance networking. So this particularly relates to the Cilium project, which I'm quite involved with and which Isovalent was the original creator of. Is anybody here using Cilium? I see a few hands. Hooray, excellent. So in a containerized world, we usually run our pods with a separate, they each have their separate network namespace. And what that means is there's a virtual Ethernet connection between networking on the host and networking inside the pod. So if I have a packet that I want to send to an application inside the pod, it arrives at the Ethernet connection on the host, it goes through the whole host networking stack to this virtual Ethernet connection, and then it goes through the networking stack again, but inside the pod's network namespace before it reaches the application. You've seen with eBPF, we can intercept network packets. I've shown how we can very easily drop them, but we don't only have that option to drop them. We can also manipulate them, we can change the address, we can send them to different interfaces. And one of the things that we can do with Cilium is we can make this networking path for packets much, much more efficient by essentially bypassing the duplicate path through the stack on the host. So we can intercept that packet as it arrives. We know that it's destined for this particular application in this particular pod, so we can bypass the host networking and send that packet directly into the pod networking namespace, making things much more efficient. You don't really need to know all the ins and outs of how that works, but what's more important is that you do get a significant performance improvement by avoiding this duplication of networking stack. So this is a post that Trendyol did earlier this year, showing performance improvements of up to 40% in their networking, and that's really using the power of eBPF. Networking is nothing if you can't debug it, and the ability to observe networking is critical. Cilium comes with a component called Hubble, which allows you to see individual network flows, so you can see those individual packets, but you can also get a picture of how those build up into communications between different services. You can get Prometheus metrics. I've got an example here showing it on a Grafana graph, so we can see things like what's our latency of different requests and response. And all of this is, again, aware of the Kubernetes identities, because you don't want to be debugging networking problems based on IP address and port number. You need to know which pods are involved, which namespaces are involved, and so on, because IP addresses are constantly reused in a Kubernetes environment. So really, eBPF is allowing us not just to improve the efficiency of networking, but also giving this really deep and comprehensive visibility into what's happening with networking. I think this might be the last practical case I was going to talk about today, is using eBPF for security. I found in last year's Dynatrace State of SRE report that 68% of SREs believe that security will be even more important in their role. Anybody here agree with that? Anybody think that security is important? I see a fair few hands. Good. So this is pretty much the same diagram I showed you really near the beginning of this talk, where eBPF allows us to attach to all these events that happen in the kernel. And really, those hardware-related events are often what we're interested in from a security perspective. We're interested in malicious network activity, or malicious memory access, or malicious access to files. So by being able to observe events in those fields, that gives us a good starting point for detecting security violations. Now, one example, a very kind of simple example, and we've kind of already touched on this, is the idea that if you have a malicious network packet, you can just drop it. We talked about that for the packet of death kernel vulnerability, that if you see a particular packet that you know is going to crash your kernel, you could use eBPF to throw that packet away. We also can use eBPF to drop packets if they're outside of a network policy. Think of this as firewalling around individual pods and services. So we can define that certain pods are allowed to talk to certain other pods, and we can drop packets if they don't meet those requirements. It gives us really fine-grained and very efficient network policy. So, security observability, we're going to observe some events, which we can do with eBPF. We're going to compare them against some policy, and the policy is saying what defines a malicious event, what makes it suspicious. I don't necessarily care about every single file open event, but maybe I do care about some particular directories or some particular sensitive files, and the policy saying which files am I interested in defines the fact that it's a security observability, not just observing everything. So we want to be able to filter all of those, let's say, file open events, and only look at the ones that are potentially relevant for security. And then we can use that to generate logs or alerts, and ultimately somebody's going to look at those and decide, well, is there a real security issue here? And if so, how did it happen, and how many of my applications are affected? Now, Brendan Gregg, who I mentioned earlier and has been incredibly influential in using eBPF tools for observability purposes, and he has basically said you shouldn't just be taking your observability tools as is and using them for security monitoring, because it would be like driving your car into the ocean and expecting it to float. And I think really what he's getting at here is you don't want to just observe all the events. You want to be able to filter them. You want to be able to, as early as possible in the process, only show the user really potentially malicious security events. You don't want to log every single possible file open event, because that would generate a lot of logs, most of which, I don't know, 99.99% of which were irrelevant. It's only the handful that are affecting, particularly sensitive files that you're really interested in. And ideally, you want to be able to filter those events inside the kernel. And that is a pretty new thing that we've been able to do with eBPF. And the tool that we're doing it with is a thing called Cilium Tetragon. So Tetragon lets us have a policy that defines the kind of events we're interested in, and it generates outputs. It actually generates JSON output, but I'm going to show you the kind of human-readable version of these events. And much like Inspector Gadget, it's also adding in the Kubernetes contextual information so that you know which pod, which namespace, and so on is actually performing these suspicious events. So, yeah, let's go here. So this should be tracing out a whole load of events. By default, Tetragon will tell us about every process starting and stopping event. And I've also got, if I can find, where's my prompt gone? I think I might have got rid of my shell inadvertently, so let's create a new one. Okay. What was I going to show? I was going to show you the tracing policy, so let's... Yeah, can't... There we go, that's better. All right. So I have a couple of tracing policies loaded at the moment, one of which is telling Tetragon to trace out any TCP connect events. So you can see here, actually, Inspector Gadget's been doing a bunch of connect events. And I've also got a policy that's looking for access to the etc password file. And if I... Now, it's only interested in Kubernetes events. So if I just look at the that file from the host, we shouldn't see any tracing generated by that. But if I do the same thing from within a pod, come on screen, behave. Let's try this, cats, etc. password. So hopefully this is going to generate some some very slow response to my typing. Hopefully when I run this, this is going to generate some trace. Yes, so there we go. So we can see Tetragon telling us that the process started to cat that file and opened that file and closed that file. Okay. Now, oops. Perhaps I want to prevent malicious activity. And I think people are quite reasonably concerned about preventative actions. They're concerned about, throwing out the baby with the bathwater. You don't want to have a policy that stops malicious activity, but that also inadvertently stops correct behavior. So because of that, we're quite often used to security tools generating a lot of information and then leaving it to kind of forensics to say, yeah, actually, no, that really was malicious. That was a bad thing. We didn't want that to happen. Something that we can do with Tetragon, and this has only been possible in relatively recent versions of the kernel, because eBPF continues to evolve in the kernel, we have the ability to not just filter events inside the kernel, but also potentially stop them by sending a kill message from within the kernel to the process that's behaving badly. So if I go back to my policy, so I need to see what it was called. Policies. Tracing. If I look at this detail of etc. password, you can see that it is matching on, don't worry too much about the details of it, but it's looking for events that relate to the etc. password file. And in fact, if it sees a write system call, it's going to send a kill signal. Now, if we tried to do this from user space, we'd edit the file, we'd make a write to change the file, and by the time a user space security application got wind of this, and if it killed the process, that write action would have already taken place. But because with Tetragon we can do it synchronously, I hope that I'm going to be able to show that it doesn't get the opportunity to take place. So let's try. Let's open a shell into this container to start with. Okay, so we can see, actually when you open a shell, it also reads the etc. password file. So that's kind of expected. Now let's see what happens if we try to edit this file. And if I put something like hello Dublin in here. Now obviously you don't really want people editing your password file. That would be a bad thing to allow. So hopefully, yeah, you can see that it got killed. We also saw the event traced out here. And if all it killed was the vi process, the editor process. If I look at that file again, let's do it with vi again. You can see that right at the top, there is no sign of that hello Dublin that I tried to write. That write action was prevented. It was killed before it had the opportunity to take place, which from a preventative security perspective is incredibly powerful. Obviously, you have to be very careful about the policies that you write to make sure that you're not, as I say, throwing out the baby with the bathwater. You need to know. But a lot of the time, we do know that we don't want anybody messing with the password file on a containerized application. That's a pretty common thing we would not want people to be able to do. So this ability to use eBPF to change the behavior for security purposes is incredibly powerful. So I think I've shown you a bunch of different examples where we've looked at observability, we've looked at networking, we've looked at security, we've looked at mitigating vulnerabilities, we've looked at all these different things that we can do with eBPF because we can dynamically change the way that the kernel behaves. We can use these tools that have been built on an eBPF platform that not only use the power of eBPF, but they also collect information about Kubernetes so that we can debug issues, we can understand the cause of issues, we have that contextual information to combine with eBPF. And we can now even use eBPF to prevent things that we don't want to happen. I showed you a few examples of projects that are from the CNCF, Cloud Native Computing Foundation, that are using eBPF. There are several more that are also starting to use eBPF now. So I think we'll see more and more projects making use of this as the kind of fundamental basis for building infrastructure tooling. If you think that was interesting and you want to dive in more, you can download the books about eBPF from isovalent.com. If you are interested in how Cilium uses eBPF for networking and observability, or also the Tetragon security project, you'll find all the information starting from the cilium.io site or Cilium on GitHub. And yeah, I hope there will be some questions. I think we've got a few minutes left for some questions. And if anything, I just hope you leave with some sense of excitement for how powerful eBPF is going to be for improving infrastructure tooling. All right. And the demo's pretty much worked, right?